Hi, welcome all to the online classes. I'm Mukesh Bhardwaj, going to present a topic on types of electric field and electric potential in uh, BTech Electronics and Communication fourth semester, subject Electromagnetic Field Theory. So, types of electric field. Types of electric field. The electric fields are of four types: uniform electric field, uh, non-uniform electric field, static electric field, time varying electric field. Uniform electric field. Uniform electric field is an electric field in which at every point within the electric field has constant electric field strength. Non-uniform electric field. A non-uniform electric field is an electric field in which at any 2 points within the electric field does not have constant electric field strength. Static electric field, the strength of electric field that does not vary with respect to time is called static electric field. This static electric field is produced by static electric charges. Time varying electric field, the strength of electric field that varies with respect to time is called time varying electric field. Electric line of forces, we know that when a unit charge or a point charge is placed in electric field of another charged particle, it will experience a force. The direction of this force can be represented by the imaginary lines. These imaginary lines are called electric lines of force. Electric lines of force are also called as electric field lines. The concept of electric lines of force was introduced by Michael Faraday in 1837. The direction of electric lines of force from positive and negative charge is shown in the below figure. For positive charge, the electric lines of force move away from the center of the charge, but in the case of negative charge, the electric line of force moves towards the center of the charge. The diagrammatic representation of electric line of force, in the case of positive charge, it is moving uh, outward, and in the case of negative charge, it is moving inward and perpendicular to the charge. Opposite charge attract each other. Two opposite charges are placed close to each other. They get attracted because the force present between them is attractive. Let us consider two opposite charges as shown in below figure. Below figure clearly shows that for positive charge, the electric line of force moves away from the center of positive charge, and for negative charge, the electric line of force moves towards the center of the negative charge. So, this is a diagrammatic representation of electric line of forces. If these two opposite charges placed close to each other, the positive charge move in the direction of electric line of force and enters into the electric field of negative charge. Here the positive charge gets pulled towards the negative charge because the electric line of force for negative charge are also in the same direction. Therefore, the two opposite charges get attracted. Like charges repel, if the two positive charges placed close to each other, they got repelled because the force present between them is repulsive. Let us consider two positive charges as shown in below figure. Below figure clearly shows that for both the positive charge, electric lines of force moves away from the center of the positive charges. If these two positive charges are placed close to each other, both the charges will try to move in the direction of electric lines of force. The positive charge at left side will try to move towards the positive charge at the right side, but the electric line of force of the right side positive charge oppose this movement. In the similar way, the positive charge at right side will also experience opposing force from left side positive charge, and both the charges will experience a repulsive force from each other. This is the diagrammatic representation of the repulsive nature of the like charges. The electric field of lines are diverted as they are more closer to the each other. Properties of electric line of force. The electric line of force starts from positive charge and ends on negative charge. The electric lines of force always enter or leave the charge surface normally. Electric line of force can never intersect each other. The electric line of force cannot pass through a conductor. When two opposite charges are placed close to each other, the electric line of force present between them will become shortened in length. When two like charges are placed closer to each other, the electric line of force present between them will become enlarged in length. Electric flux. The word flux comes from Latin word fluxus, which means flow. Anything that moves continuously from one point to another point is called flux. In the similar way, The electric line of force flowing from one point to another point is called electric flux. We can simply define electric flux as flow of electric line of force or electric field lines. The electric flux is represented by the symbol psi. Similar to the electric charge, flux is also measured in coulombs. Electric flux density, the number of electric field lines or electric lines of force flowing perpendicular through a surface area, is called flux density, electric flux density. And electric flux density can be mathematically defined as electric flux per surface area. Electric flux density is equals to electric flux psi upon surface area per to the surface area. Electric flux is measured in coulombs and surface area is measured in the square meters. Meter square has the SI unit of electric flux density is coulomb per square meter. When we say that electric flux density in an electric field is 6 coulomb per meter square, it means 6 coulomb of electric flux passes perpendicular through a surface area of 1 meter square. If the number of electric line of force passing through a given surface area is high, then electric flux density is also high. Similarly, if the number of electric line of force passing through a given surface area is low, then the electric flux density is also low. When the surface is placed perpendicular to the electric field, maximum number of electric field lines or electric lines of force will pass through the surface. So this is the diagrammatic representation perpendicular to electric field, electric line of forces. Maximum electric field is going to be passed through the area, and if the surface is parallel to the electric field of lines, then the zero electric flux is passing. When the surface is placed parallel to the electric field, no electric lines of force will pass through the surface. The concept of electric flux density can be easily understood by comparing it with the butterfly net. The amount of air moving through the net at any given time is the flux density. If the wind speed is high, then the flux through the net is also high. If this net size is made large, the air, that is flux, analogically flux through the net, gets increased even though the wind speed is same. If the net is placed in the direction facing the wind, then maximum amount of air will pass through the net. On the other hand, if the net is placed parallel to the wind, then no wind will flow through the net. The electric flux is considered as positive if the electric line of force go away from the surface. On the other hand, it is considered negative if the electric flux lines of force enter into the surface. Now, electric potential energy. Electric potential energy is the energy that change energy that charged particles such as electrons and protons have because of its own electric charge and its relative position to other charged particles. Electric potential energy is also called as electrostatic potential energy. Just like the gravitational field around Earth, there exists an electric field around the charged particle. Any objects that are placed within the gravitational field of the Earth will experience a gravitational force and force towards the Earth. Similarly, charged particles that are placed within the electric field of other charged particles will experience force. This force causes one charged particle to move away from the other charged particle or move towards the other charged particle. Let us consider a positive charge A that has electric field and small positive charge B. If a small positive charge B is placed in the electric field, the positive charge will experience a repulsive force. In order to move this positive charge B towards the positive charge A, work must be done on positive charge B against the repulsive force. This work done on charge B or energy transfer to charge B will be stored in the form of potential energy. Now we can say that the charge B has electric potential energy. The amount of electric potential energy depends upon the amount of the work done. If we release the charge B, work gets done by the electric charge and changes its electric potential energy to kinetic energy. This is the pictorial or diagrammatic representation of work done on electric potential. In order to move two or more point charge, more amount of work must be done. If more amount of work is done, more amount of electric potential energy is stored. And charged particles have the ability to do work on other charged particles. We know that energy means ability to do work on objects. Thus, charged particles have electric potential energy. Electric potential. Electric potential is the amount of electric potential energy that unit charge has within the electric field. It may also be defined as the amount of work done in moving a unit positive charge from a common reference point or from an infinity to any given desired point against the electric field of big positive charge. Any point outside the electric field of big positive charge can be considered as the reference point. Electric field potential is also called as electric field potential or electrostatic potential. Electric potential can be mathematically written as electric potential or V equals to W by Q, that is work done by the on the work done upon the charge. Let us consider big positive charge A and unit charge B as shown in the below figure. If a unit positive charge B is placed at the reference point outside the electric field of the charge A, then the force on charge B due to the charge A is zero, and charge B has zero potential at this point. In order to move the charge B towards the charge A, work must be done against the electric field of charge A. If the work is done on the charge B against the electric field of the charge A, the unit charge starts moving towards charge A. This work done on the charge B is stored in the form of potential energy. The closer the unit charge to charge A, the higher will be the potential energy. This potential energy of unit positive charge within the electric field of charge A is called electric potential. The SI unit of electric potential is 1 volt. If 1 joule of work is done on the unit positive charge, 1 coulomb, to move from a reference point towards a big positive charge against the electric field, the electric potential of unit charge at that point is 1 volt. Electric potential difference or voltage. The difference in electric potential energy of a unit charge between 2 points within the electric field is called electric potential energy or electric potential difference or voltage. It is also defined as the amount of work done to move a unit positive charge from a point of lower potential to point of higher potential against the static electric field. The point at which a unit charge has less potential energy is called lower potential. In the similar way, the point at which the unit charge has more potential energy is called higher potential. Electric potential difference is also called as voltage or electric pressure. Consider two different points A and B in electric field of positive charge Q as shown in figure first. Here point A is much closer to the charge Q than point B. Let a unit charge is placed at point B. This unit charge has electric potential of energy VB. In order to move the unit positive charge from point B to point A, work must be done on unit positive charge against the electric field. If the work is done on unit charge, the energy gets transferred to unit charge and it will start moving from point B to A. Hence, at a point A, unit charge gains electric potential energy as shown in figure 2. The amount of electric potential of a unit charge at point A is VA. The amount of electric potential gained by unit charge from point B to point A is called as potential difference. Therefore, the potential difference between point B and point A is VA minus VB. Electric potential can be mathematically written as electric potential difference V is equals to VA minus VB equals to work done per unit charge. If 1 joule of work is done to move 1 coulomb of charge from one point to the other, the potential difference between these 2 points is 1 volt. In the similar way, if 5 joules of work is done to move 1 coulomb of charge from one point of lower potential to point of higher potential, the potential difference between these 2 points is 5 volt. However, 1 joule of work is released as heat if 1 coulomb of charge moves from point of higher potential to a potential of lower potential. The electric potential difference between 2 points is measured in volts. 1 volt is equal to 1 joule per coulomb. A voltmeter can be used to measure the potential difference between the 2 points. Generally, ground or zero potential is taken as common reference point. So these are some questions related to the topic. Two identical balls have positive charge q1 and q2 are separated by a distance, separated by center to center distance r. If they are made to touch each other and then separated to the same distance, the force between them will be option A, less than before, same as before, more than before, 0. So we can make a use of the formula and calculate the result, and the C is the right answer. The electric fluid is not continuous, and all the charges occurring in nature are positive or negative integral multiples of certain minimum electric charge. This minimum electric charge is the magnitude of electric charge on an electron. This fundamental charge, to which we give the symbol E, has the magnitude of 1.60 into 10 to the power minus 19 Coulomb. So the charge on electron is minus E, while the charge on the proton is plus E. Okay. The fact that charges on proton and on the electrons are numerically equal but opposite in sign has been checked experimentally to an amazing degree of accuracy, and namely to 1 part in 10 to the power 20. Any charge q, no matter what is its origin, is given by q equals to plus minus ne, where n is equals to the number of integer, or stand for the integer value, that is 1, 2, 3, 4, and so on. When a physical quantity such as electric field, electric charge exists in discrete packets rather than in continuous amount, it is said to be quantized. This fact is referred to as quantization of electric charge. So I'm repeating that when a physical quantity such as electric charge exists in discrete or packets rather than in continuous amount, it is said to be quantized. This fact is referred to the quantization of electric charge. When suitably examined on a microscopic scale, most of the properties such as mass, energy, angular momentum, etc. are observed to be quantized. The property of quantization of electric charge has to be kept in mind while dealing with electric and magnetic problems at microscopic level. For many practical purposes or large-scale phenomena, we can ignore the quantization of charge and regard the charge as something continuous. In the discussion of classical electricity and magnetism, the quantization of charge is completely ignored. This is because of the quantum of charge, E, is so small that graininess of electricity does not show up in large scale experiments, just as while breathing we do not feel that air is made up of atoms. Just as Newtonian mechanics does not correctly describe the behavior of matter on an atomic scale, the classical theory of electromagnetism also fails to describe the behavior of charge on the atomic scale. So we simply say that q equals to Ne, where q is the electric charge of any object or body, n equals to any integer positive or negative, where minus E is the elementary charge carried by the single electron, or E is the elementary charge carried by the single proton. The charge on electron is written as minus E, and this is positive. The quantization charge first suggested by the experiment laws of electrolysis discovered by Faraday. It was experimentally proved by Millikan oil drop experiment. The total charge on object is equal to the algebraic sum individually present within the object. If an object contains n1 electrons and n2 protons, then total charge on the object is n1 into minus E plus n2 into E. For example, if the object contains 150 electrons and 200 protons, then the total charge on the object is minus 150 E plus 200 E is equals to 50. Hence, the object is positively charged. The object charge can be exactly 0E or 1E or 2E dash dash dash, or minus 1E minus 2E, but not in fractional value, that is 1 by 2, 1 by 4, and so on. Next. Now these are the some methods of charging. The process of supplying the electric charge, that is electrons to an object, or losing the electric charge, electrons from an object, is called charging. So the process of supplying electric charge, basically the electrons to an object or losing the electric charge, electrons from an object, is called charging. An uncharged object can be charged in different ways: charging by friction, charging by conduction, charging by induction. So these are the three basic fundamental methods of charging. By friction, that is by rubbing, you can charge or transfer the electron, or by charging by conduction method, or by charging through the induction method. Now let us discuss each methods of charging one by one. Charging by friction. When object is rubbed over another object, the electrons get transferred from one object to another. This transfer of electron takes place due to friction between the two objects. The object that a transfer electron loses negative charge, electrons, and the object that accept electrons gain negative charge, that is electrons. And the object that gains the extra electrons become negatively charged, and the object that loses electrons become positively charged. Thus the two objects get charged by friction. The charge obtained on the two objects is called friction charge. This method of charging an object is called electrification by friction. Now the charging by conduction. The process of charging the uncharged object by bringing it in the contact with another charged object is called charging by conduction. That means basically the conduction, you just bring any charged object to the uncharged object in contact with the uncharged object. So the charge start transferring from the charged to uncharged. It's just simply like you may call it as a diffusion, or anything which is at higher density uh, moves towards the lower density, or we can call that, suppose if you spray a perfume in a room from one corner, so that perfume spread to the another corner, because there is a low density. Wherever the low density is there, the fumes or the fragrance of the perfume moves on through the medium of air. Similarly, charging by conduction is the same process. When you bring any charged object with uncharged object in contact with uncharged object, the charge start transferring, and this process is known as charging by conduction. A charged object has unequal number of negative electrons and positive charges, protons. Hence, when a charged object is brought in contact with uncharged conductor, the electrons get transferred from charged object to the conductor. Consider an uncharged metal rod A capped on an insulating stand and negative charge conductor B as shown in figure below. This is the figure in which one rod is insulating on a insulating stand, which is totally uncharged, and rod B is charged with negative charge. When you just make rod B in contact with rod A, the charge will equally get distributed or transferred to the rod A. So this is called the charging method by conduction. If we touch the uncharged conductor A with the negatively charged conductor B, transfer of electrons from charged conductor to uncharged conductor takes place. Hence, uncharged conductor gains extra electrons and charged conductor loses electrons. Thus, uncharged conductor A becomes negatively charged by gaining of extra electrons. Similarly, uncharged conductor become positively charged if it is brought in contact with positively charged conductors. Now the third is the charging by induction. This is very important. The process of charging the uncharged object by bringing another charged object near to it but not touching it. It is called charging by induction. That is influence. By the influence of anything, if we are going to deviate or divert, then we can say that due to the induction. Consider an uncharged metal sphere and negatively charged plastic rod as shown in the figure in the next slide. If you bring the negative charged plastic rod near to the uncharged sphere as shown in figure below, the charge separation occurs. This is the phenomena of charging through induction. In figure first, plastic rod and the sphere is separated with a distance. And if we just bring a plastic rod more closer to the sphere, the negative charge in the plastic rod attracts the positive charge of the sphere towards it and repel the negative charge towards another side. And in figure third, if you just ground the sphere, the whole negative charge moves to the ground and the sphere will become positive, fully positive charge. And again in the fourth figure, you just again separate both the rod and the sphere. The positive charge in the sphere get attracted towards the plastic rod and move to one end of the sphere that is closer to the plastic rod. Similarly, negative charge get repelled from the plastic rod and move to another end of the sphere that is farther away from the plastic rod. Thus, the charges in the sphere rearrange themselves in a way that all the positive charge are nearer to plastic rod, nearer to plastic rod, and all the negative charge are farther away from it. If this sphere is connected to a ground through the wire as shown in figure, free electrons of the sphere at farther and flow to the ground. Thus, the sphere becomes positively charged by induction. If the plastic rod is removed, as shown in figure 4, all the positive charge spread uniformly in the sphere. Next, now we are starting with Coulomb's law. Coulomb's law Yes, Coulomb's law, the study of electrostatics begin with the Coulomb's law. The study of the electrostatics began with the Coulomb's law. Coulomb's law is an experimental law published in 1785 by French physicist Charles Augustin de Coulomb. Uh, Charles Augustin de Coulomb. Uh, just wait a minute. There's some problem. Yes, the study of electrostatics begins with the Coulomb's law. Coulomb's law is experimental law published in 1785 by French physicist Charles Augustin de Coulomb. This law is very important for the development of theory of electromagnetism. Uh, Charles Coulomb observed that Charles Coulomb observed that when two electric charges are placed close to each other, they experience a force. He used a torsion balance to measure the repulsive and attractive force between the charged particles. So the statement of Coulomb's law. Charles Coulomb has developed the two laws on the basis of his experiment, which are known as Coulomb's law of electrostatics. First law. Coulomb's first law states that two charged particles of same charge, positive and negative, will repel each other, and two charged particles of opposite charge, one positive, one negative, will attract each other. Okay. Second law, Coulomb's second law states that the force of attraction or repulsion, force of attraction or repulsion between the two electrically charged particles is directly proportional to the product of magnitudes of two charges and inversely proportional to the square of the distance between two charges. This force of attraction or repulsion between two charges is also depends on the medium in which the charges are placed. So electric charge is a scalar physical quantity which determines the interaction between the charged bodies. Coulomb's law, discovered in 1785, deals with this electric interaction. This law is analogous to Newton's law of gravitation. Coulomb's law was discovered by Cavendish, but this fact became more known only after 65 years of his death. According to the Coulomb's law, electrostatic force of interaction between two-point electric charge is directly proportional to the product of the charges, inversely proportional to the square of the distance between them, and acts along the straight line joining these two charges. Strictly speaking, Coulomb's laws apply to the stationary point charges. If two-point electric charges Q1 and Q2 are separated by a distance d, then the electrostatic force between the two charges is given by force is directly proportional to Q1 and Q2 upon d square, or we can say that electrostatic force is equals to proportionality sign is removed by constant k into Q1 Q2 upon d square, where k is a positive constant of proportionality called electrostatic force constant or Coulomb's constant. Its value depends upon the system of units and also on the medium between the two charges. If the point charges are in vacuum, then I'll show in the next slide. If we increase the distance between the 2 point charges, that force of attraction or repulsion present between them will decrease. In the similar way, if we decrease the distance between 2 point charges, the force of attraction repulsion between them will increase. Coulomb's law can be mathematically written as I had already, proportionality sign is replaced by k, which is known as Coulomb's constant k, and its value is depending upon the medium. So, where F equals to the force of attraction or repulsion, between the charges? Q1, Q2 is the magnitude of charge first and charge second. D is the distance between the two charges. K equals to the constant whose value depends on the medium in which the charges are placed. And K is given as 1 by 4 pi epsilon, where epsilon equals to E naught into ER. So it can be also written as K equals to 1 by 4 pi E naught ER, where E naught is known as the permittivity of vacuum. That is equals to 8.854 into 10 to the power minus 12 F by M. Or ER is the relative permittivity of the medium with respect to free space. Okay. So E naught, epsilon naught is the permittivity of vacuum and its value is 8.845. And ER is the relative permittivity of medium with respect to free space. For vacuum, the relative permittivity ER equals to 1. Hence, permittivity is equals to E naught. Therefore, the force of attraction or repulsion between two electric charges that are placed in vacuum and medium is given by, in vacuum, it is given by force equals to Q1 Q2 upon 4 pi epsilon naught d square. Or in any medium, it is represented as force equals to Q1 Q2 upon 4 pi epsilon naught ER into d square. Now, before moving to electric field, that is the next topic, in continuation to the Coulomb's law. Coulomb's law in vector form having the great importance. So, as we know that the like charges are attracting each other, and unlike charges are attracting each other, like charges are repelling each other. Consider 2-point charges Q1 and Q2 separated by some distance d. If the product of the magnitude of charge is greater than 0, that means both are positive, or if the product are negative, then the charges repel each other. On the other hand, if we say that the product of two charges is less than 0, charges are dissimilar, then the charges attract each other. So, as we know, the force is a vector quantity. So, the electrostatic force or the Coulomb's law, or that is given as force equals to K Q1 Q2 upon R square, is a vector quantity. And by calculating the resulting force, keep the vector theory very clear in mind, because whatever the resultant force, we have to mention the direction of the resultant force when a system of charges are taken up. And if we ask to find out the what is the charge or what is the force on the one charge due to all of the charges and the resulting direction of the forces, then the vector theory must be very clear to us for calculating the force. The SI unit of charge is Coulomb. Now, if you had gone through the gravitational field or gravitational forces or gravitational theory, we find the formula of electrostatic force and the gravitational force is almost similar. In addition to the electrostatic force between two charged bodies, there are also exists a gravitational attraction between them. Uh, so, points of similarity while doing the comparison of electrostatic and gravitational forces, both these forces are central forces. That is, they act along the line joining the centers of the two interacting bodies. Both the forces obey inverse square law of distance, as you had seen in the formula. Both are conservative forces, that is, the work done by them does not depend upon the path followed. Both the forces can operate even in vacuum. Now, points of dissimilarity. While the gravitational forces are always attractive in nature, the electrostatic force may be attractive or repulsive. While the gravitational force does not depend upon the medium, the electrostatic force definitely depends upon the medium. Electrostatic forces are extremely large as compared to the gravitational force. The fact that electrostatic forces are much stronger than the gravitational force is clearly revealed from the following illustrations or some illustrations which we'll see later on. Now, starting with the topic that is electric field. Electric field, the region around a charged particle within which other charged particle will experience an electrostatic repulsive or attractive force, is called electric field. Electric field is also called as electrostatic field. The electrostatic force or electric force is exerted by the static electric charges, that is electrons and protons. Next. So, electric field, as you see in the pictorial representation of the charge, that is positive charge and negative charge is showing to you in the diagram, and the rays are moving perpendicularly away or towards the charge. So we can say these moving lines which are in the perpendicular from the charge are known as electric field of lines. Okay. So now the electric field strength. The strength or intensity of the electric field at any point within the electric field is called electric field strength. To describe an electric field, we must specify its strength. The strength of electric field at any point within the electric field is determined by placing the unit charge at that point. When the unit charge is placed in electric field, it will experience an electric force. The electric force is either attractive or repulsive. The amount of electric force acting on a unit charge placed at any point within electric field is called electric field strength or electric field intensity. So, more specifically, we can say that there is region of space around a charge of a system of charges within which other charged particles experience electrostatic force. This region is spoken as electric field. Thus, a particle is said to be in an electric field if the particle experiences a electrostatic region. Theoretically, theoretically speaking, the electric field extends up to infinity, but practically, the electric field does not show detectable influence beyond a certain limited distance. The electric field strength or field strength or electric field intensity or electricity is the ratio of the electric force exerted or experienced by a positive charge particle to the magnitude of the charge Q naught on the particle. So we can say mathematically E is equals to force upon Q naught. Since Q naught has been taken to be positive, therefore the direction of electric field be the same as that of force. So we can conclude that electric field intensity is also a vector quantity. It is also clear from the definition of electric field that electrostatic force on a negative charge particle will be in the direction opposite to that of the field cell. It is further clear from the definition that electric field intensity is a vector quantity whose magnitude and directions are uniquely determined at every point in the field. Thus, electric field is a vector point function. It must be clearly noted that electric field is external to the test charge. That is, electric field is neither the field produced by the test charge nor it is supposed to include any contribution from the test charge. In fact, electric field exists whether some test charge is placed in the field or not. So, we can say that if the amount of force acting on a unit charge at a given point is less, then electric field strength at that point is less. In the similar way, if the amount of force acting on a unit charge uh, on a unit charge on a unit charge at a given point is high, the electric field strength at that point is high. Electric field strength or intensity is a vector quantity. It has both magnitude and direction. Electric field strength can be mathematically defined as force per unit charge. As we know that force is measured in newtons and charge is measured in coulombs, hence electric field strength is measured in newtons per coulomb. Types of electric field. So there are basically four types of electric field. The electric fields are of four types: uniform electric field, non-uniform electric field, static electric field, time varying electric field. Uniform electric field. Uh, so I would like to continue this lecture, the types of electric field or the particular topic that is types of electric field in the next lecture. Uh, till to now, thank you. Thanks a lot. Have a nice day.